In this video, we are going to talk about something called moments. So a moment is sometimes called a torque. A moment makes something rotate, or tends to make it rotate if it can. Bridges and buildings can't rotate, so we need to understand moments and how a moment can affect a object that we want to be static and not moving. So here's a long list of the things that we want to take a look at. So we're going to define it first, and then we're going to talk about the units. We're going to define what's a positive versus negative moment. We're going to go do a simple example, then a slightly more complicated example, then another example. Then we'll talk about something called rotational equilibrium, which is when all the moments sum together in such a way that the object does not rotate. So first, a moment is a force of a force. So we have a force right here. A moment of a force is a measure of the tendency of the force to rotate the body. This is a wrench. I think all of us have probably used a wrench at one time or another in our lives. And if you pull out here perpendicular to the arm of the wrench, then you're going to tend to cause rotation. And that is a moment. Some terminology. Well, we have a pivot at the nut here, or the bolt head. We've got a lever arm, which is the distance between the pivot and the application of the force. Then we have our force coming down here perpendicular for now. And we have a distance d of the lever arm, which is d. Yeah, so the lever arm distance is quite important. Here is the definition of torque. It's the product of that distance d times that force F. As long as the force is perpendicular here, we don't have to worry about any trigonometric functions, so we'll keep it at that. This is a simple multiplication here. So M is equal to d times F. Very simple calculation. In terms of the units, well, in English customary or imperial, we have the force is in pounds, the distance is in feet, so we get pound-foot. That is a unpleasant system to work in. For SI, we have the Newton, we have the meter, and then we have the Newton times the meter. So a Newton meter is a force. You would say that as Newton meter. You wouldn't turn that into a joule. Remember that when we define work, a Newton times a meter is a joule. But in this particular case, we're not involving work, so we would just call this a Newton meter. How about the directional rotation? Well, we're going to be working in a 2D plane when we're doing our analysis, and the bottom line is that if we have a counterclockwise, if a moment causes a counterclockwise rotation, that moment is positive. Clockwise, it's negative. So you just got to remember that. One way to help you remember that is to use the right hand rule. So if you curl your fingers to match the direction of the rotation, like this person is doing, the thumb is pointing up if it's positive. Down, it's negative. So in this particular case, you can see he's grabbed it around the here. Sorry, the thumb goes in the direction of. Curl your fingers to match the direction of rotation. Yeah, that's it. Curl here. Whoops. And then your thumb points in the positive direction. So if I'm looking down from above, you can see that this is going to be a counterclockwise. Yeah. Why am I pausing there? That's usually pretty straightforward. We'll see that it's pretty straightforward. Here's another case of the right-hand rule. Maybe a little easier to understand because it's coming from above. So if we have this situation here where we come down here, then you can see the hands go around the direction, the fingers go around the direction of the rotation, and the thumb points in the positive direction. So this particular one would be positive. Similarly, if you have to rotate it your fingers so that it's in the direction of rotation. You're going to get a negative, points away from you, so it's negative. It'll be straightforward to understand that. Okay, let's do a calculation. We have our wrench here. We have a moment arm of 9 inches. We have a force of 20 pounds. So the magnitude of the moment is just the product of those two quantities. So that's going to be 9 inches times 20 pounds. And you can see right here they change the inches into feet. So you're going to want to do that. So 9 inches is 9 divided by 12. That's 3/4, so 0.75 feet. So 20 pounds of force times 0.75 feet is going to give me 15 foot-pounds. But I need to make sure I understand the direction, so we're going clockwise here. And so this would be a negative torque, negative 15 foot-pounds. And a longer wrench, we're going to get this is the exact same problem, just the moment arm is up to 1 foot. And we get a bigger moment. So you all know that if you have a really long moment arm and you push on here, it's going to be a lot easier. So a bigger moment makes it easier to rotate something. Okay, here's a different type of problem. So we've got an L-shaped wrench. The bottom line is that the torque is equal to the distance here, which is 3 inches. We take it into a foot here, 0.25. And then we do the product, so we get, ignoring the direction for a minute, we have 20 pounds of force. We know that. That's the easy one. But the distance is this perpendicular distance. So imagine the force is in an infinitely long line here, and it happens to be applied here, but its perpendicular distance to the pivot is 3 inches. So that's the distance you use. So this would be minus 5 foot-pounds, negative because we're going clockwise. So that may take a little time to get used to, but I think it'll be clear. And then this guy here, well, the force is perpendicular to this distance straight out here, and that is what, 18 inches or 1.5 feet. So there's our 1.5 feet. We have 20 pounds, and again it's negative because we're always going clockwise. So this would be 30 foot-pounds. So for the distance, for the moment arm, you wouldn't take some sort of diagonal here. It's the perpendicular distance of the direction from the direction of the force. Okay, here's a problem. So we have this, we're sailing a ship, and we push down here with 100 newtons. We're into metric now. And the distance from the pivot to the application of that force, so the moment arm is 50 centimeters. So I have, which is 0.5 meters. So my moment is just 50 Newton meters. It's a product of 100 times 0.5 meters. So there's a lot of unit conversion here, so be aware of that. So 50 Newton meters, great. Okay, so that's nothing new. What about if we have something here? So imagine that we pull out at an angle of 50 degrees with respect to the horizontal here, then what is the torque, our moment? Well, we have to find the projection of that force on to the perpendicular line from the moment arm. So this one is going to be, you can do the trigonometry here. It's going to be 50 times the sine of 50 degrees. So you really need to be comfortable making that trig calculation or conversion, and you're going to see that once you go through and work through here, which I want you to do, you'll see that the moment is only 38 Newton meters, whereas before we're going straight down, we got 50. So the more we pull away from the direction that's perpendicular to the moment arm, the less torque we get. That's hopefully intuitive from what you've seen before. What is equilibrium? Well, that's what we're going for. So the state of the body or physical system with an unchanged rotational motion. Two cases for that: object is not rotating, or it's spinning at a constant speed. We're going to ignore this one. Technically that is equilibrium, but we're only going to go for the case where the object is not rotating. So in either case, all rotational forces are balanced. The sum of all the moments about any point, any particular axis that you can choose, it's up to you where to choose that axis, is zero. So we have the sum of m is equal to zero. So we add all these m's up and they must equal zero. And of course, many of them are negative. Many of them are positive. So the negatives and positives cancels out if we want to have equilibrium. So we have to have moments acting, tending to make it go clockwise and counterclockwise, and balance those out is what we're going to spend our time doing. Okay, quick example. This is a seesaw. These little teddy bears are here. This dude looks a little bigger. And so if we go to the next one, we see that this teddy bear weighs 40 pounds. This teddy bear is some distance away from the pivot. This teddy bear is a baby teddy bear, and he's 25 pounds, but he's 4 feet away. So and of course, a little teddy bear is a positive moment because he tends to make it go counterclockwise. Big teddy bear is a negative moment, so he tends to cause it to go clockwise. So again, for equilibrium, we want the teddy bears to balance. Sum of the moments equals zero, so m1 plus m2 equals zero. And then we get this equation here. All right, and then if we just put in the d's and the f's, we have one unknown, which is d2 over here. It's right here, and if we just do the arithmetic, we're going to find that in order for this to be rotationally in rotational equilibrium, static, we need to have d2 is equal to 2.5. So he needs to be closer to the pivot because he's bigger. And so hopefully all of you have played on this as a child or an adult, and you know how this thing works. Got to be closer if you're bigger. This allows us to show that analytically, and you'll need to be very comfortable with that too. Here is another problem. We have a beam here, and we're going to be doing a lot of problems like this. Let's see, what is that? I don't know. Oh yeah, the blue is just the support, so the green is the reaction forces. The reaction forces are forces by the earth or by a support laying on the earth on the object, on the beam here. So we have reaction forces. They call it RAY because it's point A here. They call this RBY because it's at B. They don't use the F sub RBY. That would be a complicated notation, so they just use R for the force. So those reaction forces exist, and we've got a birthday present here, but it's not centered. It's over here a little closer at only 3 feet away, and the whole thing is 10 feet. So would you agree that RAY is going to have to support more of this load here of 35 pounds because it's closer over there? Well, the question is, well, just exactly how much? And so we can use this formalism here for rotational equilibrium. Sum of all the moments about any point that you choose must be zero. So it says select A as the pivot. You can choose anything, but let's choose A. Now, any force acting at A is going to have zero moment because the moment arm will be zero for any force acting at A. So they just go out here. So the moment due to B, which is the reaction force here, making it go that way, which is positive, counterclockwise, plus the moment due to the present setting there. Must add to zero, so we get these equations same as before, and we just put in the numbers, and what comes out is that the reaction force is 10.5 at B. Where's B? This side. So it's considerably less than half the force here, right? If it was right in the middle, you would expect that 35 divided by 2 would be supported by A and B, but that's not the case because this guy slides over. And finally, 24.5 for A, and if you add those together, you better get 35. Yeah, you do. So that's the kind of problem we'll be doing. Maybe one more. Okay, this is a truss, and we've got our reaction forces at A and D. We've got additional load forces. This could be due to wind up here at 500 at point B. Point C, we've got maybe a truck sitting there. And we're going to maybe get into this in a little more detail later. Let's see, how far do I want to go with this one? I am going to just show you the slides and encourage you to maybe think through, because it's really, these are not that hard. Uh, Sum of the moment about point A, we've chosen a 0, so you add up all the moments. Well, there's a moment due to F sub B, F sub C, and also the reaction force over here, R sub dy. And you do the algebra, and you're going to get that R sub dy is equal to 640 pounds. So this guy over here is 640. So interesting, yeah. So it's more than the load here that's going straight down, and that's due to this horizontal force, which is, it's causing rotation in the negative direction, right? So that's going to put a force onto D. And so that's how we use moments. We're going to use these quite a bit. We're going to use them in conjunction with the forces. We're going to sum all the forces in the XY direction, set them equal to 0. We're going to sum all the moments about a point, set those equal to 0. Those are the equations of statics, and those are the ones that are going to allow us to solve a lot of complicated problems in statics and bridges and buildings and things like that. So make sure you're comfortable with this content.